Hello, everyone. How's it going? My name is Hagen, and I'm a graduate student in the Building Energy and Environments group within Civil, Architectural, and Environmental Engineering. I'm here in the U test house running a few experiments for you all to help you understand a little bit more about the fate and transport of indoor air pollutants, mass balances, and the pollutant that we're going to be using today to talk about CO2. The U test house is a standalone house that the BEE group has up at Pickle Research Campus that has been gutted, repaired, and wired up to run multiple experiments from how cooking a Thanksgiving meal might affect your air quality to calibrating low-cost sensors in kind of a near-real environment. You'll have to excuse the mess. We fired our interior decorator, so things have gone to shambles. But I'll do my best to point out the devices and components that we'll be using today for our experiment. But before we do that, I'm going to give you kind of a rundown of the various experiments that we'll be running today so that you have that before we get started. First, we're going to try and estimate a source term. In this case, me. As you all are most likely aware of, when we exhale, we emit a fair amount of CO2. David can run you through the math, but if you know the volume of the space and you have a series of CO2 measurements, you can calculate the amount of CO2 that your source is emitting. Second, we're going to evaluate the so-called well-mixed condition that many researchers assume, but can oftentimes not be the case. When we say something is well-mixed, we are saying that the concentration of the pollutant does not vary in space. Or in other words, the concentration is the same everywhere. To test this assumption, I'm going to inject CO2 into the room and measure the concentration in different parts.
Assuming I don't asphyxiate myself, we should have data to analyze the well-mixed condition. After that, we're going to do something similar, but this time I'm going to use these babies to help induce mixing. These fans should help give us a better look at whether or not the well-mixed condition is valid, at least in our space. Lastly, we're going to calculate an air exchange rate. CO2 is the perfect gas to use for this because it is inert, meaning it doesn't tend to react and or adsorb to materials very easily. Again, I will inject CO2 into the space, but this time I will turn on the AC, which should pump in fresh air and help remove and or dilute the CO2 in the air with this fresh air from outside. If we assume the flow in is equal to the flow out, we can use the CO2 decay to calculate an approximate air exchange rate.
I almost forgot. I have to tell you how we're going to measure CO2. So this here is what we refer to as the Bevo beacon. The beacon was developed by yours truly, alongside help from others in the Intelligent Environments Lab under Dr. Nagy's guidance. The Bevo beacon measures a variety of indoor environmental quality parameters, but we'll focus on just CO2 for today. I recently installed these small screens right up here, so we can see the measurements from each of the sensors. The data will also be logged right here on the device itself, which will be provided to you so you can crunch the numbers. Now we have nearly 50 of these devices, but we don't need to use all those, so today we'll just use a few, which I have strategically placed around the test house so we can monitor the CO2 concentration at the source and at other locations around the room.
And that's it. So let's get started.
So I hope you enjoyed my facial expressions as we time-lapsed through that video. And hopefully in the top right corner you saw the CO2 concentration. That was from the reference instrument. And that data is being reproduced here for you in this figure. I started the experiment a few minutes after I had walked into the test house. So the background concentration was about 450 parts per million. And then as I continued to work in the test house and walk around and do a few different things, the concentration was steadily increasing because I was exhaling CO2, as I mentioned before. And then here at about 9:45 is when I started to do jumping jacks. And there's a little bit of a lag before the instrument picks it up, and that's of course because the CO2 had to travel to the inlet of the reference machine. But then there's this very noticeable increase in the CO2 concentration, and even afterwards a little bit, because I was still exhaling. I was still at a more active level, and so I was still exhaling that CO2 at a greater rate. And so you actually have the opportunity to back out two emission rates. You have one from a more sedentary activity level, and that is here at the very beginning. And then you also have this option to use this best fit line here to kind of estimate an emission rate for me as I'm doing some low level activity.
Now I'm going to inject CO2 into the kitchen right behind me, and we're going to measure the CO2 concentration right at the exhaust. In addition, we're going to measure at the places I pointed out earlier, kind of in the corners and neighboring area of the space, and see how long it takes the concentrations at those perimeter areas to match up to the concentration that we're measuring right at the exhaust of the cylinder.
This is the cylinder I'm going to use to inject CO2 into the kitchen. So if I open it here, hopefully you hear that. And so now these tubes, one of them is the CO2, it's this one right here. And we are injecting CO2 right here into the middle of the space. Hopefully it should come in here and kind of spurt out. And we should see the concentration rise.
Here I am showing you the data from all of the beacons that we're measuring in those various parts of the test house, as well as in black here is the outdoor concentration as measured by another beacon that I placed outside the test house. I tried to color each of these lines based on their proximity to the source, so the darkest red would be the one that is closest to the source, whereas the bluest blue, if you will, would be the beacon that is furthest away from the source. The beacon that was closest to the source is colored here in dark red, and you can see it had the greatest response to the CO2 that was being injected because it was right by that source, and so it felt that concentration more than any of the other sensors because it was more concentrated at that location. These other three beacons here, the one near the source, the one at a nearby table, and the one on the floor, which is actually probably just as close as that nearby table, they all experience a similar concentration, but definitely not nearly to the extent that the one at the source does, and that's because the concentration gets a little bit diluted as it travels to those locations. And the one that was furthest away in the corner was the one that actually showed the smallest response to the concentration that was injected, because by that point the CO2 has been diluted, it's been mixed with the larger volume, and so we don't see as great of a response here, and it only barely gets maybe 100 or 200 parts per million higher than what the steady state concentration is most likely going to be. So here we peak at about 1,100 ppm, but it seems to stabilize maybe around 900 parts per million. So we only see a difference here of the peak to the steady state of about 200 parts per million, whereas the one that was right by the source gets almost up to 2,000, which means we see a difference in about 1,000 parts per million from the peak concentration to what the steady state concentration is most likely going to be. You can also see that it takes maybe 30 minutes, maybe 40 minutes from the start of our experiment to reach a consistent measurement between all of these beacons. And so hopefully when we try the mixing experiment, we should see that it takes a little bit less time to reach a more consistent measurement amongst the beacons.
Now I'm going to inject CO2 into the same place back in the kitchen, but this time I'm going to turn on those box fans as well as the ceiling fan to help induce some mixing, and so hopefully the concentrations at those perimeter areas should match up with the concentration measured right at the exhaust much quicker. And that will get us at the well mixed condition, and we'll see how long it takes for that well mixed condition to actually be valid.
Here I am showing you results from the experiment when we had the fans mixing the CO2 concentration around the test house. It's important to note that we start at about 400 parts per million higher than we did in the previous experiment where we started around 500. However, we still reach a similar concentration as we did last time, at least at the source. We reached 2000. But in this case, almost all of the other beacons reach a very similar concentration, meaning we have a much greater mixing going on in the space. All of the beacons, regardless of their distance, right? Remember, dark red is closest, blue is furthest away. They all have a very similar response, but it's actually very nice because you see this lag here, and that's due to the travel time that the CO2 takes to get to each of these beacons. We see the beacon closest to the source responds the quickest because it's going to see that concentration first before any of the other beacons. This nearby table, which we kind of saw in the last experiment, is actually closer than this near source beacon, has the second fastest response, and then the three other ones have a very similar response time. However, again, we see that because this beacon that's furthest away is furthest away, it still takes a little bit more mixing. We didn't have quite enough mixing in the space to have all of these concentrations rise at the same rate. But it's safe to say that after maybe 20 minutes that we're reading a very similar concentration amongst all of our beacons, where last time it was about 30-40 minutes, and now we can see at 40 minutes we can see that these beacons are essentially measuring the same thing as they approach the steady state concentration.
Now we're going to try and calculate an air exchange rate in the room. So again, I'm going to inject CO2 into the room. I'll have the box fans on to help induce mixing so that we have a near equal concentration throughout the entire room. And then I'll also turn the HVAC fan on. The fan should help to pump outdoor air inside to help remove the excess CO2 that's built up.
These are the measurements we get from the reference instrument when trying to gauge how well the AC is at removing CO2 from the space. So when I talk about the fan, I'm not referring to the fans that are inducing mixing. I'm talking about the whole house fan that is ventilating the space in this case. So here we start around 700 parts per million again. We have a nice, somewhat steady increase as I pump CO2 into the space. We get to about 2300 parts per million, and then I shut off the injection. The box fans are still mixing the concentration in the space, so we should be seeing a general constant concentration across at least that living room area where I was in. And then here is where we see the contribution from the AC fan, the mechanical ventilation, as it's pumping in fresh air from outdoors and pushing out and or diluting the CO2 concentration that's in the space. And we see a good effect here, a strong effect here, and that's because we have such a high concentration, and the outdoor air, of course, is somewhere down here at 400 parts per million. So we're going to see a more dramatic decrease, at least when we start at higher concentrations. And then as we get lower, we don't see as much of an effect. And that's also primarily due to the AC fan that's in the test house. It's not as strong as probably your more traditional house because, like I said earlier, there's been guts and repairs, and some of the inlets and exhausts have been plugged up in the test house. We don't get as much mixing as we might like from that AC fan, but you can still see that it's contributing a little bit here, and hopefully we'll be able to see a difference between this mechanical ventilation and what happens when I open up the windows and let natural ventilation take place.
Now we're going to calculate an air exchange rate for natural ventilation. In this experiment, I'll have the box fans on, I'll inject CO2, we'll mix the CO2 into the room, and then I'll open all the windows in the space. That should give us an idea of how good the natural ventilation is in the space, and we can compare the air exchange rate we get from the natural ventilation to the one we got from the HVAC fan, which would be the mechanical ventilation.
In our final experiment, you can see the natural ventilation taking place. So again, in black here, I have the reference instruments measurements of the CO2 concentration in that living room space. Here we start at our highest concentration, so about 1200 parts per million. I inject CO2 again here. We get up to about 2000 or so parts per million. I stopped the injection about here, I let everything kind of mix a little bit more, and then a minute later is when I opened up all those windows, and you can see the most dramatic, if you will, decrease in CO2 concentration that we've had. And that is because we had all of this fresh air from all of these windows that were pumping out the CO2, and it wasn't even a windy day. So you can imagine if it was a windy day and we had a greater cross flow, it might not even take the 10 minutes it took to go from its peak to about a background CO2 concentration. It could take only 5 minutes, and this could be almost a vertical line that goes straight down to the background concentration. So in this case, you can see that natural ventilation played a much larger role in removing that CO2 than the mechanical ventilation did. And so hopefully you should be able to see that this air exchange rate, this ventilation rate we got from the natural ventilation case is going to be dramatically higher than the ventilation rate we got from the mechanical ventilation.